All right, so we started talking about important sampling in the last video, and just to recall a little bit, recall that in important sampling, we are interested in estimating an integral theta, which is basically the expectation of h under f. So it's integral h times f of x dx, and by rewriting this integral as this expectation, where G over here in the denominator is a proposal or an importance distribution, then what we can do is we can get samples from G, IID samples from G, and take an average or Monte Carlo average of these weighted H's. Right? So if I call W to be F by G, right? Then I can use this W over here to say that theta hat G, my important sampling estimator, is nothing but the sample mean of H of Z times WZ. Okay, and this is my important sampling estimator, and we discussed that it's nothing but a weighted average. Now let's do a simple example. Let's say that the goal is to estimate the moments of a gamma distribution. Okay. And so it could be any moment. So suppose we want to estimate the kth moment of a gamma distribution or a gamma random variable. Now, let small f be the density of this gamma, which is, so the density of this gamma is this part over here, which is beta to the alpha by the gamma function of alpha, x to the power alpha minus 1, and e to the power minus beta x. Okay, then theta is nothing but integral 0 to infinity x to the power k times f of x dx. All right, this is theta. Now suppose we set G, my proposal or importance distribution, to be an exponential distribution. Now, the support over here of f is x greater than 0, right? And so I should choose a proposal distribution such that its support is also greater than 0. And the support of an exponential random variable is in fact the positives, right? So now let's say I get, I forgot IID here. Let's say I get Z1 up to Zn, IID from exponential lambda. Then my important sampling estimator again is nothing but the sample, a weighted sample average. So theta hat n is 1 over n times summation t going from 1 to n, h of z, f of z divided by g of z. Okay, and I can plug in what h and f and g look like. And when I do this, well, h of z is z to the power k, so I get that. Right? And then I have this coming from my f, this coming from my f, and then the denominator over here comes from my g, my exponential distribution. Right? That gives me my estimator, and that's it. This is my estimator. I can go ahead and implement this. We already know that we can generate samples from an exponential random variable using the inverse transform method, so we're all set. Okay, so what I do now is in the simulation below, I'm going to set alpha to be equal to 2. This is the shape parameter. Beta to be equal to 5. This is the rate parameter of my target gamma. And I set lambda to be equal to 3. This is the rate parameter in the exponential. Okay. And what I want to do is I want to estimate the second moment. So k is equal to 2. Okay. So luckily I already know that the second moment of a gamma random variable is alpha by beta squared plus alpha by beta whole squared. So expectation of x squared under f is exactly this. Now, the way this will be helpful is that what we'll do is we'll obtain estimators of this using important sampling and check how close they are to actually this particular number and compare it. Okay, so let's get started. Recall again, I want alpha to be equal to 2, beta to be equal to 5, lambda to be equal to 3, k to be equal to 2. So first I set my seed so that you can repeat this process and get the same answers as I did. So alpha is equal to 2, beta is equal to 5, k is equal to 2. Now, the truth or the true value of theta is alpha by beta squared plus alpha by beta whole squared. right? So that's the true second moment. And when you run this, you'll see that the answer for the true value of theta is 0.24 for these choices of alpha and beta. Okay, now we're going to gear up for the process of importance sampling, for which I set lambda to be equal to 3. Now, n is 10 to the power 4, so it's 10,000. And I generate my samples from the exponential. Now, we've learned multiple methods to generate samples. Implementing them by ourselves can be fairly slow. And so what we'll do from now on is although we've learned all the theoretical framework and methodological and computational way of generating samples from the exponential distribution, we'll just use REXP, which is a function that gives us random draws from an exponential distribution with a given value of the rate. So I ask it to draw 10,000 samples from this exponential. Then I calculate func. Now func over here is going to be basically f of zt by gt, g of zt times h of zt. So I will calculate this in a way that's conducive for vectorizations for all the values of the z's, of the z's that I have sampled from SAM. So I take h of z, which is z to the power k, over here. So that's SAMP to the power k. Then f of z is a gamma distribution density function. So I do d gamma of the SAMP. SAMP because I have to evaluate it at the zt's. So d gamma of the SAMP with the required shape and rate divided by g, which is d exponential of SAMP with the rate being equal to lambda, because that was my choice of proposal. And then once I've gotten all of these funcs, right, then I just do 1 over n summation, 1 over n summation t going from 1 to n. And that means I want to just take an average, right? So I just take a mean of func, and that should be my best guess for theta, which in this case is 0.385123, which is fairly close to the actual value of theta. Now again, in this case, I actually know what that integral is. I know what the second moment is, and I don't actually need importance sampling. But this is for demonstration to let you see how we can use importance sampling. Now, our estimate is fairly close, like I said, right? So we're very close to the actual truth. Now we can also visualize and compare how the reference density F, the target density, and the importance density G actually look, okay? So which means that I can actually see that the target density is in the black, which is the gamma 2, 5. And the reference or the proposal density is this exponential, which is exponential 3. And these are all the values that are actually drawn from this exponential distribution. Now you'll notice that this exponential is going to sample a lot of values from around, this area, right? So these values will be sampled a lot because they're in an area of high probability for this exponential. On the other hand, values over here will not be sampled that often because they are in an area of low probability for this exponential. Okay, and we see that this actually matches fairly well the situation that we're in, right? So where the exponential distribution matches the gamma distribution fairly well, which means our weights associated with the weighted average is going to be fairly well behaved and fairly large. So we do want the target and the exponential to be not exactly the same, but fairly close to each other. And we'll comment on this a little bit more in the next video. Okay, we've done an example now. So now the question is, what kind of properties does the importance sampling estimator have? We constructed an estimator of theta in the very beginning of the last video using just simple Monte Carlo. Okay, and we motivated that there may be a way of doing better than simple Monte Carlo, and which is why we started looking at importance sampling. So in order to do that, we need to sort of establish certain properties of the importance sampling estimator. We need to see what kind of bias or expectation does it have. We need to understand what kind of variance does this have. And so that's really what we're going to be doing next. So the first theorem towards this cause is of showing unbiasedness. So the important sampling estimator theta hat G is unbiased for theta. Now, it's a pretty straightforward proof. To show that an estimator is unbiased, I just need to show that the expectation of that estimator is equal to theta. And that's all I need to show, that the expectation is equal to the desired quantity. So consider expectation of theta hat G, right? Now, in order to calculate this expectation, I can first just plug in what theta hat G is. So this is expectation of 1 over n, summation t going from 1 to n, h of z, f of z divided by g of z. Now, the 1 over n can come outside the expectation, not an issue. And expectations are linear in the sense that I can exchange summations and expectations. And so over here, I exchange them, and then I get 1 over n summation t going from 1 to n of expectation of g, h of z, f of z by g of z. Okay, but now this thing over here, I notice is that these are all identically distributed. So this expectation again is the same for all of the t's. So I can just write this as summation of h of z1, which means that when that all of these things are the same, so this summation and this n just get cancelled. Okay. So, and finally, I just need to write down what this expectation looks like. Well, it's an expectation of h of f by g, where the z's are coming from g, right? So because the z's are from g, this is nothing but the integral of h of small z, f of z, g of z times g of z dz. G, because my sample z is coming from g, not from f. When I do this, I let g and g get cancelled, right? So I just get integral h of z, f of z dz over script x, which is in fact the support of f, right? And so this turns out to be equal to theta. So I showed that my estimator is in fact equal to my desired quantity theta, and hence we have unbiasedness, right? That finishes that result. So this is a great thing, because what it's saying is that the estimator has nice properties. It is in fact unbiased. And then particularly we have that by the law of large numbers, theta hat g will converge to its expected value. Okay, so theta hat g is going to converge exactly to its expected value, which is nothing but theta. Okay. So this means that as we get more and more samples from G, from our proposal distribution, our estimator gets better and better and increasingly closer to the truth. And for any given value of n, for any given number of samples, the estimator will be unbiased as well. Okay. So let's actually go back to our gamma example and try to sort of visualize, verify this convergence. And the way to do this, again, the convergence result was the following, that theta hat p converges to theta in probability, right? This is the convergence result. And so what I do is I generate it, and this convergence is as n tends to infinity, okay? So as I get more and more samples, so this should be theta g. Right. So as I get more and more samples on this side, this converges closer and closer to theta. So I'm going to choose a very large sample size, which in this case I choose 100,000 or 1 lakh samples. Okay. And I get random draws from exponential. These are my z's. Okay. Then again, I calculate my func, right? My sequence of f of h times f by g. But I don't average them just yet. What I do is I do a running sum, a running average. So on the x-axis, what I'm going to plot is the sample size on the x-axis and the corresponding average from these number of samples on the y-axis. So this will plot a running average. Okay. And what I get is this line. So in the red horizontal line over here is the true line, is the true value of my target quantity theta. And in black, I get that for any number of samples, let's say some, 50,000, 5,000 number of samples, it goes and finds what is the sample average or what is the Monte Carlo estimator at all of these values and then plots them over here. Okay. And we see the law of large numbers here kicking in. We see that in the beginning, yes, there's a little bit chaos, there's a little bit sort of zigzag motion, and then eventually things stabilize. Right? So that's an illustration of what the law of large number means in this case. Now we can also try to verify via simulation that the fact that theta hat g is indeed unbiased. Now this is a tricky concept, but we can try. The thing is that unbiasedness is a concept that is pertaining to the expectation of a random variable. Okay, so unbiasedness means that the expectation of theta hat g minus theta is 0. So somehow I need to show that this expectation is 0. But the expectation of a random variable is related to its behavior in repeated sampling, in repeated data, right? It does not necessarily say anything about our current sample as much as it says about what are the kind of patterns theta hat g will look like. So just to demonstrate the concept of unbiasedness, this is not done in practice in importance sampling. I will reiterate that. But just to demonstrate the concept of unbiasedness, what I do, I'll mimic the situation of getting this expectation by estimating this expectation with a sample average itself. So what we do is we will repeat the simulation above multiple times. We'll repeat it some r times, which means r small r different times. I will go to my exponential random variable, exponential distribution, get capital N samples, calculate the importance sampling estimate of theta, and that will be theta hat g1. Okay. Then I will go back and do it again. That will give me theta hat g2, and this will I'll keep doing r different times to give me multiple theta hat g's. And then by definition, if r is large, then if I take a sample average of theta hat g minus theta for all of the k going from 1 to r, then this average should be close to its actual expected value. Right? So this diff r should be roughly close to 0 in case of unbiasedness. Okay? So let's check that. Right? So let's verify that it is indeed unbiased. So n is equal to 10,000. So in every time I do the importance sampling, I get 10,000 draws from the proposal distribution. I repeat this process 1,000 times. So small r is 1,000. And in all of those 1,000 times, I will obtain theta hats and store them in S. Okay. Now for A in 1 through small r being 1,000, I calculate my importance sampling estimator. I get my importance samples, my proposal samples. I calculate func. I take the mean of all the func. So this calculates, just to recall, this calculates f of zt, h of zt, g of zt for all t's, and then this part over here calculates the mean of these. And that's just going to be my importance sampling estimator, which I will save in S at the 8th spot. Okay. Now from here, all of these S are nothing but theta hat 1, theta hat g1, theta hat g2, up until theta hat gr. Right? So I will subtract the truth from them, which I remember is 0.24, and I'll take the mean of those truths, and this should be equal to diff r. This is the diff r quantity, which should be equal to 0. And when I actually print the value, what I get is this looks like 2.7001 into 10 to the power minus 5. So that means this is actually 0.000, one more 0, 2700126. So it's a value very, very close to 0. Now, obviously, I can't calculate the exact expectation in simulation. If I could, I would get exactly 0. This is my estimate of that expectation over here. and that estimate of that expectation turns out to be 0. Okay, but I'm a statistician. We're working in a statistical computing course, and we should then never be happy with a point estimator. As in, we shouldn't be happy with a number for a guess for theta. We also want an understanding of what kind of values does it take, how much variability does it have, right? So it is essential to understand, quantify that variability. So our estimator is theta hat g, and we want to know whether it's stable or is it going, do we expect it to be erratic, right? We might also want to make confidence intervals, let's say, around my estimator theta hat, right? But does a central limit theorem hold? Previously in simple Monte Carlo, we relied on the central limit theorem. But does it hold in this case or not? We're not sure. So we have to understand that. So first note that the variance of theta hat g is nothing but variance of the actual theta hat g. So I just plugged in what the form is. And just like before in the simple Monte Carlo, I can pull this outside to make it become 1 over n squared. And then all of the variances of these things are all the same. So this just becomes 1 by n variance of h of z1, f of z1, g of z1, which now I will call sigma squared g by n. So sigma squared g over here is nothing but variance under g of h of z1, g of, f of z1 by g of z1. Now, a central limit theorem will also hold, because this is just an actual average. A central limit theorem holds if this is finite, right? So if sigma squared g is in fact finite. So the question is, when is sigma squared g, when is this finite? And the following theorem is very simple, very straightforward, helps us understand when it's finite. So suppose that first thing, that the variance of h under f is finite. So the variance of h under f, which means the Monte Carlo variance, is finite. So first we have to assume that the actual quantity I'm interested in, the variance of that under our target distribution is some finite quantity. Okay. Now if g is chosen, now remember we are choosing an importance distribution g. And we could choose any distribution we want. And as the choice of the importance distribution changes, the quality of the estimator changes. No matter what the importance distribution is, it's always going to be unbiased. We just proved that. But we do need to ensure that the variance is well behaved, and the variance can be different for different values of g. Okay. So if g is chosen such that the supremum of f by g is less than equal to sem m, which is finite, then sigma squared g is finite, which means the simple importance sampling estimator has a finite variance. Now recall that this ratio was also in accept reject or rejection sampling, right? So this is a familiar quantity. We did see this. In order to implement accept reject, we needed supremum of f by g to be bounded by some c. And now I'm calling that f by g sup to be bounded by some quantity m. So let's start by proving this. So first we note that if the second moment is finite, then the variance is finite, because the variance is nothing but the second moment plus the first square of the first moment, right? And so if the second moment is finite, that's all I need. So consider the second moment of hf by g, where z is from g. Okay, so we consider that. Then expectation of hf by g whole squared, which is the second moment. So again, this is the second moment of h z f z by gz when z is from g. Okay, then this is nothing but integral of hz squared fz squared gz squared with respect to gz dz. Now 1g and 1g over here get cancelled, so I just get h squared f by g times fz/dz. Okay, but I know that f by g over this whole support is uniformly bounded by m. Right? So over all the values that we're integrating over, f by g remains bounded. So this is less than equal to m times integral of hz squared fz/dz. Right? But this is nothing but the second moment of h under f. So this is m times the second moment, which by assuming that the variance is finite, we have also assumed that the second moment is finite. So this has to be finite. Okay. Now notice that we're asking the questions if the variance is finite or not, which means there will be situations when the variance will not be finite for the importance sampling estimator. But if I choose my proposal distribution in such a way that sup of f by g is less than equal to m, some m that's finite, then my importance sampling will give me finite variance. It may not be a small variance, but it will give me a finite variance. Okay. All right. So again, if an accept reject on the same support is possible, then the variance of the importance sampling estimator is finite. And now that we know the condition for it to be finite, we can now say that now we have a central limit theorem that can hold. Again, recall this is my sigma squared g. So if sigma squared g is finite, then I get my CLT straight away. Now, just I wanted to highlight that this is a sufficient condition only. Okay, which means that this need not hold true. Which means, sorry, that if this condition is not satisfied, it doesn't mean that the variance cannot be finite. It can still be finite, but this is certainly a condition that's sufficient to show. Okay, let's go back to our gamma example and see what happens. What we can do is we can try and verify again via simulations that for this choice is sigma squared g going to be finite or not. Now, recall that we've actually done this, the gamma and the exponential example when we were doing accept reject. So recall from the accept reject example for gamma alpha comma beta, where alpha was greater than 1, so first alpha has to be greater than 1, and exponential proposal such that lambda is less than b. So we recognize in accept reject that alpha had to be greater than 1 and lambda had to be less than b. And when that holds true, then an accept reject can be implemented so that f by g is bounded. And this means that when lambda is less than b, there exists a finite m. So I need to choose my lambdas. I need to ensure that that holds true. Now, in the last implementation, we did choose lambda equal to 3 and beta equal to 5. Okay, so that's the example that we've been looking at should produce a finite variance estimator. Okay, now again, we can verify this with the same idea as before. Now, our sigma squared g again is variance of h of zt, f of zt, g of zt. Right? This is our variance, and again, this is a concept that is not necessarily true about this particular sample that I've gotten, but a general behavior of this estimator, which means I can't measure the variance potentially just from the samples over here. I will have to do something repeatedly. So we can verify this by using our replicate. So we get theta hat g, theta hat squared g up to so on. And noting that the sample variance of these R estimates should be sigma squared g by n. The reason is that the variance of theta hat g1 or any of these is sigma squared g by n. This is what we had shown a few minutes ago, right? So if we go back, we showed, no, not here. If we go back, we showed that variance of theta hat g over here is sigma squared by n. So I want you to make sure you remember the by n part over here when you're talking about the variance of an importance sampling estimator. Okay, so if I just take the sample variance of all of these things, then that should be sigma squared g by n. And that's exactly what I get is my sample variance, the variance of all the s should be sigma squared g by n, which is 1.2 into 10 to the power minus 5. So if I look at n times this sigma squared g by n, which should just be sigma square is fairly small, 0.1204. Right? Okay. Now, let's just see what happens when we change things up a little bit. Let's see what happens when lambda is equal to 10. Now, when lambda is equal to 10 over here, right, then lambda is greater than beta. So if lambda is greater than beta, I know AR, AR is not possible, accept reject is not possible. But then again, my function, my theorem is not a necessary and sufficient theorem. So it is just sufficient, implying that it is possible for the variance to be finite, even when this does not hold true. Okay. Right? So for this choice, this is in fact equal to infinity, but this does not imply that sigma squared g will be infinity, since the above theorem only provides a sort of a sufficient condition or in one direction a necessary condition. Okay. Okay. So now we look at when accept reject fails. Lambda is greater than beta. We know accept reject fails. Let's see what the variance is there. Lambda is 10. I repeat this process again, this whole thing of generating all of these theta hats. Okay. And then my mean of all of the theta hats, my S, is fairly still close to 0. The mean of the S minus the truth. If it's unbiased, this should be close to 0. And I get minus 0.013. Not too bad. But variance of the S, or sigma squared by G by N, is 0.026. Now this looks small, but remember this is divided by N. So if I multiply by N, then the variance of H of ZT, F of ZT by G of ZT is estimated to be as high as 264 in this case, which is really large, right? So we can see that the variance blows up. Now, we can't conclude whether the variance is infinite or not, because it can't be infinite in our samples that we've gotten. But it certainly is very, very, very large. But the other thing I want to highlight is that the variance of the estimator doesn't have much to do with the fact of the convergence of the estimator. Okay, so the law of large numbers still holds true even though the variance is possibly infinite. So moreover, in this example, the convergence plots can be analyzed as well. Note that convergence in the law of large numbers, we do not require a finite variance. So the convergence will still happen. Our important sampling estimator, despite its variance, whether finite or infinite, will definitely converge to the true quantity. But how many samples will it need to converge will heavily be impacted. Now, so for the same lambda equals 10, for the same n to be equal to 10 to the power 5, and then I also consider n to be equal to 10 to the power 6, I repeat the simulation again to get a running plot of my convergence estimator. And I get something like this. Okay, in 10 to the power 5 observations, I get my estimator. Yes, it is very erratic, but then it's sort of slowing down, right? It's slowing down. It hasn't quite reached the red line yet, but eventually we hope it will. And certainly when we get to 10 to the power 6, yes, it's erratic, but it then converges up. And then if you go to 10 to the power 8 or 9, it will eventually converge. Again, not necessary that it happens anytime in finite size, because it's an infinite result. It will happen eventually is the idea. Okay. Right. So what some questions to think about for you in the simulation. Try to rerun this and check what happens when beta is equal to lambda. So our choice of the lambda that we're doing is in fact equal to beta. And a question I always want you to think about is, why would a CLT be useful here? If we have a variance already, why is a central limit theorem in addition to a CLT going to be important? And then how do we check whether this important sampling method is better than IID Monte Carlo? How do we actually check that? How do we quantify that? How do we quantify it better? This is something we'll do in the next video. And so it'll be useful for you to think about it right now.